So today we are setting up a super exciting experiment, and what you can see behind me is kind of the basis of it. So at the back you can see a bit of a rubbly patch, and this is a whole lot of snow that we've moved. Lots of mahi going on out there with the snow shovels. And so we've got about a 10 centimetre average snow thickness sitting there. And then in front there's a patch that we've removed all of the snow off this. And so essentially what we're playing with here is the light levels that are getting through down to the bottom of the sea ice and the platelet layer below. And why we're doing that is because in the bottom layers of the sea ice and the platelet ice, we are sampling cores. And in those cores, we are looking at microalgae and bacteria, which are kind of the foundations of the food web. And they, especially microalgae, rely on sunlight to create energy, and that then gets passed on to other critters that eat them. So what we're trying to see is how these shifts in snow cover are going to affect that community that's living in that ice down there. So when you change the light levels available to these microalgae, it can, within an individual cell, cause them to change the quantities of lipids, of certain types of fatty acids that they are producing. So essentially, some of these can act as kind of a sunscreen for a microalgal cell.
These are ultraviolet or UV beads, and they'll change colour based on the amount of ultraviolet radiation they're receiving. So let's take these outside and see how they behave in sunlight. So already you should be able to see these starting to change colour. We've got a lot of ultraviolet radiation here in Antarctica, both directly from the sun and reflected from the snow, and so these change colour probably a lot more rapidly, I would say, than they would back in New Zealand. But even then, if you take them outside, you'll see a change within 5 to 10 seconds. And you can time the change, and you can use color pickers on any sort of photo editing app to help determine, how much they have changed color, or, by which point they've reached a desired color. So the polyethylene beads have something called spirocompound molecules embedded inside them. And the energy of the ultraviolet light causes a bond to break in those spirocompound molecules. This causes the molecule to rotate slightly, which causes light to be absorbed and reflected differently, which is why we see a color change in the beads through exposure to ultraviolet light. Okay, so this is the view through an ultraviolet camera. And what we're seeing is what the world would look like in ultraviolet. So the camera's sending out ultraviolet light, and that's being reflected from the surroundings and detected by the camera. And so you probably notice that my freckles look a lot darker in ultraviolet light, and that's because freckles are pockets of melanin, a pigment in the skin that absorbs ultraviolet radiation, and by absorbing ultraviolet radiation, it helps protect our cells from the damaging effects of ultraviolet radiation, which can lead to skin cancer. And so in Antarctica, it's really useful to have great sun protection. So I've got here a bottle of SPF 50, because not only are we dealing with the ultraviolet radiation directly from the sun, we're also dealing with the reflected ultraviolet radiation from the snow. And so it's quite possible to get burning on the underside of your nose, and I've even heard about people getting burnt on the roof of their mouths due to that reflected ultraviolet radiation, which is directed upwards, which is kind of unusual for us. So I'm going to put on some of that SPF 50, some of that sunblock, and you'll get to see what it looks like in the ultraviolet spectrum. Got to make sure I get the underside of my nose. All right, so I can feel now that this is, you know, if you were seeing this under the normal visible light spectrum, then this sunblock is all blended in, so you wouldn't see much white residue on my face now. And yet that sunblock is so good at doing its job because in the ultraviolet spectrum it's black, it's absorbing that ultraviolet, which means it's not able to penetrate further into your skin where it could damage the DNA of your cells. All right, isn't that cool? This simulation was created by the King's Centre for Visualizations in Science, and it's a really useful way of looking at ozone in the atmosphere and seeing how different wavelengths or frequencies of light interact with those ozone molecules. So we're looking at ozone here, which is three molecules with three atoms of oxygen bonded together, and we can see that currently we're in the visible part of the spectrum, and as we change that and look at different wavelengths or frequencies of light, then we can see how those interact with the ozone. So if we bump it up to infrared and wait for one of those photons to interact, then we see that the pattern of vibration or oscillation of the atoms in the molecule changes. We can adjust it again, and again we see that it creates a different vibration pattern in the ozone molecule. But something quite interesting happens if we drop it down to ultraviolet. So here's ultraviolet A. Okay, so that brings us back to this sort of behavior. And if we put it to ultraviolet B, then we see that the ultraviolet radiation of that particular frequency or range of frequencies knocks one of the oxygens off the ozone. Now, what's happening there is that the ozone is effectively protecting us from the ultraviolet, some of the ultraviolet radiation from the sun. Now, naturally in the atmosphere, that oxygen will then reform into ozone, but some chemicals such as chlorofluorocarbons that we released into our atmosphere prevent the ozone from reforming, and that can have some quite harmful implications for us. This NASA visualization shows how ozone concentration across the southern hemisphere has changed since 1984. And so with this, you can see where the lower concentrations of ozone are, specifically across Antarctica. In 1974, it was discovered that chlorofluorocarbons were causing a significant depletion in atmospheric ozone concentrations, and that started some nations banning chlorofluorocarbons and led to the Montreal Protocol. So in the same way that the ice was protecting some species of microalgae from potentially harmful ultraviolet radiation, the ozone layer also protects other life on Earth from some of that ultraviolet radiation reaching us from the sun.